All right. One of the big things that we want to be able to do is we want to be able to calculate how the concentration will change with respect to time. Okay? We have developed a tool to tell us how the rate changes with concentration. We want to convert that into a relationship between time, because remember the rate had time in it, right? The change in concentration over the change in time. And mathematically, the process is quite simple if you know calculus, and otherwise it's essentially impossible to do. So what we're going to do is do some hand waving, and I'm going to give you the results of some calculus, some integrations is what we would do. We take the equation and we integrate it, which is a calculus process that you don't need to worry about at this point, okay? And what we're going to do is we're going to find out how does the concentration vary with time for our different order of rate laws. So far, the rate laws that we've pretty much looked at, or the ones that you need to know, are zero order, first order, and second order. Those are the three orders that you are likely to come across on a test. Okay? So let's start with first order rate laws. They are the most common. And a first order rate law is one where you have you have your rate law is such that you have the chemical, the reactant is to the first power. So it turns out that this chemical reaction is a first order reaction. We could have gone through and done the method of initial rates to figure that out. Okay? But what we need to be able to do is to look at a relationship between time and concentration. So what we want to do is we want to look at, collect data that is time versus concentration. And we want to figure out, be able to, from that time and concentration data, figure out whether the reaction is a first order, second order, or zero order rate law. Questions?
The rate law is that.
Uh-huh.
What's the other rate when it has time on the clock?
Right. So this is what we call the rate law. It's probably more properly called the differential rate law. And so we're going to be talking about the integrated rate law. So the integrated rate law is essentially taking this mathematical equation and integrating it, which is a calculus process that you don't need to know how to do.
Do they achieve the same thing?
They tell us different things. This shows how rate is related to concentration. The integrated rate law shows how concentration is related to time. Okay? So in this one, our variables are essentially rate and concentration. In the other one, our variables are going to be concentration and time. So the way that we are going to do this is by looking at graphs. Okay? And the most common type of problem is where you are given some graphs and asked to figure out what is the order of this reaction, or asked to sketch, not calculate, but sketch graphs based on knowing what the order is. Here is the important piece of information. For a first order reaction, a graph of the natural log of concentration versus time gives you a straight line. So that's only for first order. For first order reaction, for a first order rate law, a graph of natural log of concentration versus time gives you a straight line. How many people have heard of natural logs before? Okay, so a handful of you. Logs are a way to deal with exponents. Okay, a way to deal with exponential numbers. You will learn all about them in Algebra 2 towards the end of the year. Functionally, for our purposes, it is a button on your calculator. Okay? And it literally is, if you take out your calculator, there's a button that says ln, okay, natural log. Okay? So, for our purposes, we need to be able to hit the button on our calculator. What this graph represents is taking this concentration, okay, and you do ln, you press the ln button, which is the natural log button, you type in the concentration, you hit enter, and so we're going to have a new set of data. We've imagined doing a new column here, which is the natural log of concentration.
Wait, how do we do this?
So,
Press the button next to 4,
yeah.
and then you put 1.
So at time 0, if you did ln of 0.1, you get something like 3.8 or something like that, right?
Right there.
Negative 2.4, 2.2, 2.3, something like that. Great. So see, that's what they did. Here's our negative 2.3. At time 50, you do the ln 0.0707.
How do you do that?
Fine. Look at your calculator. See the ln button? Press it. Type 0.0707. Hit enter. And you get this number here. How does it know? All right. So, real quickly, real briefly, what this is, okay, what you're doing is your calculator is finding out E to what power gives you this number. Where E is a special number, 2.3, it's kind of like pi in terms of it's a special number. It's the natural number. It turns up in all kinds of natural systems like growth rates for bacteria and how plants behave and all kinds of crazy things. Turns out to be this like fundamental constant of the universe. So, what the calculator is doing when you're doing ln of some numbers, it's saying, hey, E to what power would give me this number? That's what it's calculating. Okay? The log is the more generic form of this. Typically log base 10 is what we use, what we might see. Although in general in natural sciences, in the work that we do, E turns out to be a better base. So that's why we typically use it. But log is, the log of some number is 10 to what power would give you that number. That's what the log fundamentally is. If you want more details, ask your math teacher. Make them deal with it. So, mathematically, we can take this differential rate law, and if we graph the natural log of these concentrations versus time, we say, hey, look, that's a straight line. That tells me that this is a first-order reaction. Okay, if I graph natural log versus time and I get a straight line.
Is it always going to be a straight line?
If it's a first-order reaction, then natural log of concentration versus time gives you a straight line. If it's not first order, it's not a straight line.
What's it going to be? Is it
We'll see. I got 2 other swings to show you. If you're graphing a linear function on a log plot, you get a curve. We're graphing an exponential function, so what we get is a straight line. Okay? So if you graphed this data, if you graphed concentration versus time, this would be curved. By changing it to natural log of concentration, we get a straight line. Questions?
The natural log of concentration.
This is, we took the natural log of each of these concentrations and graphed it versus the time. That's this plot right here.
Wait, so is it at different times?
Right. So look, each point, right, represents the natural log of the concentration at a given time.
When would there be a zero order thing? I mean, wouldn't everything...
We'll talk about why that happens. It can totally happen. It does happen. Generally happens where things are surface catalyzed, where that's typically where we see the zero order reaction.
So, like, for all of, or for any compound, kind of like, is it going to be a straight line? And how does that work?
We'll get there.
What you're talking about.
Let me show you the setups. We got to learn what gives us straight lines for each of the different orders before we can sort of look at how would we do this. Okay? Right now, what I want you to get out of here is that if you are graphing some data that has to do with concentration and time, you're going to graph it a couple of different ways. If you graph it the natural log of concentration versus time and you get a straight line, that tells you that it's first order. Okay? Which means that the differential rate law looks like this and the integrated rate law looks like this. Okay? Our integrated rate law is the natural log of concentration is equal to negative kT, that's our time, plus the natural log of our initial concentration. The natural log of our initial concentration.
What is it not?
Hold on.
You said that if you graph concentration and time, and it's a straight line, then it's always first order?
Yes. If you graph the natural log of concentration versus time, and get a straight line, it's a first order.
Okay, and then what's the bottom one?
This is the integrated rate law for a first order reaction. Okay, integrated rate law for a first order reaction. This K here is the same K. This is the same K values. Okay, that's the rate constant.
Are you saying natural law or natural log?
Natural log. L-O-G.
What is the zero coefficient of?
So the 0 here means initial, or starting at time equals 0.
Why did you put a negative?
That's the way the math comes out. It's a calculus. If you did this, if you integrated this, this is what you would get.
That's the rate of first order.
This is the integrated rate law for a first order reaction. Okay? Does the form of this equation look familiar to anybody? It's the equation of a line, right? Y equals mx plus b. And b is the y-intercept, right? So that's the time 0. Time 0 is where we started. Y equals mx plus b. Okay? How exciting for us. All right, so first order, we graph natural log versus time and got a straight line. Second order reactions. In the second order reaction, this happens to be a second order reaction. We know that we're going to just have the concentration of the reactants squared. If you graph, okay, you collect concentration versus time data. If you graph the natural log of concentration versus time for a second order reaction, is this a straight line? No, it is not. Because you'll see. It's going to change. So this is the natural log of concentration versus time. And we said, hey, it's not a straight line. I guess it's not first order. So let me try and graph the inverse of concentration versus time. So I've graphed the inverse of concentration versus time, and I said, hey, look at that. It's a straight line. That tells me that this is a second order reaction. If you graph the inverse of concentration versus time, and you get a straight line, you know that it is a second order reaction, and the integrated rate law for second order looks like this. We have the inverse of concentration, time, and again the inverse of concentration at time equals 0. Does the form of that equation look familiar to anybody? Y equals mx plus b. And does that make sense? Yeah, we got straight lines. So we should expect the equation to be the equation of a line. Y equals mx plus b.
Okay, when you say the inverse concentration, is that the inverse concentration log?
No, just the inverse concentration. 1 over the concentration. So this data here is if you say the right time equals 0, the inverse of the concentration was 100. So our concentration was actually 0.01. But we did 1 divided by that concentration, and that gave us this data point. Not logs, nothing like that, just inverse. For the first one, it was logs. So what we do, the process is going to be take the data, graph 3 different graphs, see which one gives you a straight line. Because if you graph the inverse of concentration over time and you get a straight line, you say, hey, that's second order. But if it's curvy, you know it's not a second order. If you graph inverse of concentration versus time. So you kind of got to guess and check until you get a straight line. And typically, they don't ask you to actually do these kind of graphs, do all these things on the test. Usually they either give them to you or they ask you to just say, hey, it's second order. What would a graph of, inverse? And you go, it would be a straight line. What would the graph of this be? Oh, it would be curvy, stuff like that.
It's always going to be positive for second order and going negative for first order?
Yes, this would make sense because the concentration of our reactants are going to go down, which means the inverse value is going to go up.
And so for first order, it's always
We would expect it to go down. Yep. All right, last one. 0 order rate laws. This happens to be a 0 order reaction. Okay? It has to do with the way the reaction takes place. We're going to learn all about that next week. But suffice to say, this is a zero-order rate law. The rate of the reaction is essentially a constant fixed value. It does not depend on the concentration. For zero-order rate laws, you simply need to graph concentration versus time to get a straight line. So, we have three potential graphs. If you graph concentration versus time and you get a straight line, you go, oh, it's zero order. If you graph the natural log of concentration versus time and you get a straight line, it's first order. If you graph the inverse of concentration, that is 1 over concentration, versus time and get a straight line, it's second order.
How do you know what K is and T?
So, in all of these, if you look at the equations, K is the slope. Right? If you look at the three equations, and there are three equations, here's our integrated rate law for zero order, concentration versus time. Notice the slope, negative K. And for first order, the slope was negative K. And for second order, well, you find the slope of the line.
Do they give you the line?
Depends on the problem. Typically, they could do that. Yeah, they could give you the data points and ask you to find it.
But if they give you like a reaction, then you say
No, if they just give you a reaction, you can't do any of this with just looking at a reaction. Reactions by themselves do not tell you any of this stuff. There have to be data. Whether it's concentration versus time data, or if you could do the method of initial rates. Remember, once you know what the order is, that instantly tells you what this equation is. Right?
What's the units for K and zero order again?
The units for K in a zero order are moles over liter seconds. Yeah,
Oh,
moles over liter seconds.
well, because
It works. Look, here, right, this drops out, and rate equals K, so K has to be moles over liter seconds. Here, you're taking moles over liter seconds times seconds, so you have moles over liters plus moles over liters equals moles over liters. That works.
So that one's the integrated rate law for.
Recall, this is the integrated rate law for zero order. This is the differential rate law for zero order. Sean? The O or the zero, this zero is an exponent, because this is a zero order rate law, so this is to the 0 power. This one is a subscript, and it means starting point or at time equals 0.
So use the first rate laws and try to explain what the differential
We call these ones are called differential. These ones are called integrated rate laws.
use the differential ones to find the actual rate.
There's several different ways you could do that, but yes, if you want the rate, you typically need the differential rate law.
Which one's the differential rate law?
To see how concentration varies with time, you use the integrated rate law. All right, so here is a typical type of problem. Okay, here's a typical type of problem. We're talking about the dimerization of butadiene. Okay, what does dimerize mean? Forms out of two smaller ones. Okay, so two small molecules react together to form a larger molecule. That's what dimerize means. Mers are small units. Di means two. Two mers, two small units joined together. So we obtain the following data. Here is time versus concentration information. Okay, time versus concentration information. We want to determine the order of the reaction. So, your first thought might be, hey, I know how to determine order of reaction. I need 3 different trials, and I'm going to do the ratio stuff. And then you go, wait a sec, they didn't give me any of that information. They gave me concentration versus time data. So I can't use the method of initial rates. Can't do the stuff we did yesterday. I have to do something new. I have to graph this data, and I have to see what gives me a straight line. So I'm going to create a chart. I'm going to take this data, and I'm going to calculate the natural log of the concentration, and I'm going to calculate the inverse of the concentration. And those are the things that I need to do to go through and actually calculate what my graphs are going to be. I'm going to go through and I'm going to calculate those pieces of information. Okay? You rarely have to do this on the test. I haven't seen them actually make you do this on the AP test. Okay? But IB test doesn't cover any of this stuff at all. Sorry.
Are you gonna make us do it on our test?
No, I won't make you do this. I mean, I think they discuss things like this. That's why I'm showing you to make you understand where it comes from. This is the part that they do make you do. If you had this data and you did a graph of concentration versus time, you'd get a graph that looks like this. Here's concentration versus time. Okay? That's this first set of data. And if you graphed the natural log of concentration versus time, you'd get a data like this. And if you graphed the inverse of concentration versus time, you'd get a graph like that. What is the order of this reaction? Second order reaction. We can tell that because inverse concentration versus time gave me a straight line. That's what tells me that this is second order. Okay, that's what tells me that this is second order. Questions? Well, yeah, it doesn't have to be perfectly straight. In general, we're collecting real data, and things aren't perfect because there is always some error involved in the thing. But it's going to be pretty close to straight and significantly straighter than these guys. You don't have to worry about that. It's not something you need to worry about. They're extremely rare for reasons that we're going to learn about next week. Yeah, third order and higher are basically, they basically don't happen. I mean, extremely unusual.
So how did you get that first graph? I get this.
So this graph, I said, hey, let's graph concentration versus time.
Which is for 0, right?
So just
I just graphed it.
you just dig
At time equals 0, 0.01. At time equals 1,000, 0.006. At time equals 2,000, 0.00459.
That's for 0.
and the other ones you have to do stuff with.
You calculate the value, and then you graph it versus time. That's it. It's graph concentration, graph the natural log, press the buttons on your calculator, get these values, graph them. Graph the inverse, again, button on your calculator, x to the -1 or whatever, and graph that, see which one gives you a straight line. In general, the problems are, hey, here are some graphs of data that we got. What is the order of this reaction? That's a very typical type of problem to see.
So is that like what you're gonna ask us?
That's what is going to be asked on the test, yeah.
Great.
Okay?
Well, did we ask to determine it, like, you want to give us the graphs, and then we would have to, graph them
That is very unlikely to happen on the test. I've never seen that happen on the AP test. So the way that they would ask that question is they would say something like this. Hey, this reaction of butadiene is a second order reaction. Draw sketches of concentration versus time, natural log of concentration versus time, and inverse of concentration versus time.
Why would they want all of those in the second order?
Because they want to make sure that you know that this should be curved, and this should be a straight line. And that's really what they'd be looking for. They want to see curve, straight line. And then not like calculate it all out, sketch.
So it's just like straight.
Straight, curve, and you'd be fine.
What exactly, how would you define order?
The order of the reaction is to what power is the concentration raised in the rate law. And what does it mean is how important is that chemical in the reaction? The real physical, what happens when they collide, I'm going to teach you next week. I promise it will make a lot of sense. Okay, it turns out to be really simple. Okay? But I don't want to get a whole lot into the collision theory stuff right now. This is all of this was developed before people really had a great understanding of what happens when the molecules hit each other. Okay? Because this is all empirically derived. We're just collecting data and trying different things and see what happens.
I don't understand what numbers you put in to find
So the number that goes in this brackets is this concentration. So you take the natural log of this concentration, gives you this number. Take 1 divided by this concentration, gives you this number. Yeah. Remember, the square brackets mean concentration of. That's really important. Square brackets we use to represent concentration of. All right. Yeah, you take these concentrations, take 1 divided by them, invert them. Or to the negative 1 power, same thing. All right, so here's a summary. 0 order rates, okay, 0 order, and we only look at 1 reactant at a time in most of this stuff. So 0 order, rate is equal to a constant value. Integrated rate law is concentration versus time gives you a straight line. The slope is equal to negative k. And this equation right here is what we call the half-life equation. I know everybody in here has heard of half-life before, okay? Both in middle school and certainly in math classes as you're getting there, right? Advanced biology. Half-life is how long does it take for half of the stuff to react. Okay, for our purposes in chemistry, it's how long does it take for half of the stuff to react. So you can see that in a 0 order reaction, it depends on how much you start with. And in a 2nd order reaction, it depends on how much stuff you start with. What's unique about a 1st order reaction, notice that your initial concentration is not in here. Half-life for a 1st order reaction is independent of how much you have. 1st order reactions dominate chemistry, okay? Dominate most of this kind of chemistry. And most of the time we care about half-lives, it's going to be a 1st order half-life. It's going to be one where this is all of our nuclear decay, okay? All those kind of nuclear decay processes. It's going to be a 1st order half-life. And the only thing that really matters is the rate constant k. So what's interesting about this is most of the time they don't actually ask you to use this equation. You can generally figure it out from the data that they give you. Like they'll give you a graph and they'll say, what's the half-life? And you say, well, I started at 1. I just need to find out where did it get to 0.5 and find out the time. It's not like you have to use the equation. Most of the time they just give you information. As long as you remember what half-life is, you don't even necessarily need to use these equations. Okay? Another interesting thing, you can always derive this value from this. You take the integrated rate law, and what you do is you substitute in for A, you substitute in 1/2 of A naught. Because the half-life is the time it takes to go from A naught to 1/2 of it. Remember, A naught is where did we start? The time to get to 1/2. This 0.693, that's the natural log of 1/2. Okay, that's all it is. Because when you rearrange this equation, there's some nice properties of logs that cause the A naught to drop out, and you're left with a natural log of 1/2. And I can show you, if you're really interested in that, when we go through it, I'm going to give you a problem where we'll look at it. I'll go through it a little bit, but it's not that important for the AP test, and definitely not important for the IB test. Yes, if you're doing math stuff where it doesn't matter how much you start with, then it's 1st order. Yes. If you're using an equation like this, that's 1st order. I don't know what that means. That must be some sort of math thing.
You always have the initial in all those.
Right. If your equation doesn't change depending on how much you have, it's a 1st order reaction. Okay? So, primarily interested in being able to identify the graphs, knowing how to go, if I give you a rate, can you give me the integrated rate law? If I tell you it's 1st order, you need to be able to give me this equation. Where might we find this equation during a test? On the useful equation sheets. So we really just need to be able to recognize what it means. Okay? Do you need to memorize this equation? No, you do not. Okay? You do not need to memorize that equation. It's on the useful equation sheet. Okay? You need to know where it is. You need to be able to recognize it.
Okay, so for example, in a reaction you find K, right? And then if you do the integrated, the K is still the same.
K is the same number. Yep, exactly right. You stick a negative in front of it.
And the T is just time.
T is time. And what gives you a straight line in the first order?
If it's like,
Graph what versus what?
the in, ooh,
Did I just stand in front of it? Yes, I did.
Law of natural concentration.
Natural log of concentration gives you time. That you need to know. Inverse is second order. Those, you need to know that. That's the key piece to know. Memorize this line. Zero order, concentration versus time. First order, natural log versus time. Second order, inverse versus time. That's the key to doing the problems we are likely to see on the test. Okay? When you're fertilizing the field, knowing how the concentration changes with time is critically important. But it turns out that simply knowing the integrated rate law isn't enough. Simply knowing the K value at one particular point in time isn't enough. Because the K value, the rate constants, change with temperature. Understanding that is what we're going to do next week. Okay? Excellent.